So let's first. Okay, so let's finish up equivalence classes. So this is finishing up 9.5. So at the end of last lecture, we basically introduced equivalence relations. We discussed about how equivalence relations are relations on a set A, that is a subset of A cross A, which are reflexive, symmetric, and transitive. We went through a couple examples. We went through a whole lot of non-examples so that you could see what all of the um, properties looked like kind of on their own, right? What's a reflexive but not symmetric and not transitive relation, things like that. And then near the end yesterday, not yesterday, near the end of the last lecture, we got close to discussing kind of the way that these equivalence relations kind of break up sets in the sense that you can associate subsets called equivalence classes to every element in the set. We're going to explore that further today and kind of finish that off. And the first part of that is to prove the following theorem. Okay, let R be a relation on A, or an equivalence relation. Then the following are equivalent. So the following are equivalent. The first thing is that A is related to B. The second thing is that the equivalence class associated to A is the same as the equivalence class associated to B. Remember, the equivalence class associated to A is the set of all S in A such that AS is in R. So this is just the set of things that are related to A. Right. And then the third is that the equivalence classes A and B have non-trivial intersection. Okay. So if you remember, when we're doing theorems like this, where you're trying to show that several conditions are equivalent, it is sufficient to prove things in a cycle. That is, to prove that these are all equivalent, I'm going to show that 1 implies 2, then I'm going to show that 2 implies 3, and then lastly I'll show that 3 implies 1. So that's the strategy of the proof. And what this theorem is going to tell us is that the equivalence classes that you associate to an equivalence relation, perhaps the property that we'll use the most is that if you have two equivalence classes associated to A and B, which are related in your equivalence relation, then their intersection not being empty is the same as them being the same equivalence class. Okay, so this will help us understand partitions in a little bit. Okay, so let's prove this. So first I'm going to show that 1 implies 2. And remember this definition. So I'm going to assume that AB is in R, and I want to show that A is equal to B. Now, what are these equivalence classes? These equivalence classes are subsets of A, capital A in this case, subsets of capital A. So how do we show an equivalence of subsets? Well, we prove it by a double inclusion. I'm going to show A is contained in B and B is contained in A. So we show uh, A is contained in B and B, or the equivalence class associated to B is contained in the equivalence class associated to A. We want to show a double containment, so we start out with any element of A. So let S in the equivalence class of A. Then, by definition, AS is inside the relation. Moreover, AB is inside the relation by assumption. By the symmetry of our relation, so by symmetry, we also know BA is inside the relation. And if I have BA in the relation and AS in the relation, what can I also say is in the relation? By transitivity of my relation R, if BA is in R and AS is in R, then BS is in R. Thus, S is in the class. Thus, S is in the equivalence class of B. Right? This is the definition of what it means to be in the equivalence class of B. B comma S is in the relation. So I've shown that for every S in A, S is also in B, and the other direction is the same. Okay, so I'm only proving one of the containments, but the other containment is the exact same argument. So what we're left with is we have a double containment, thus the two sets are equal. And that finishes the proof that 1 implies 2. Let's show that 2 implies 3. So we assume that A is equal to B. Show that A intersect B. Sorry, I keep on saying A and B. This should be assume that the equivalence class of A is equal to the equivalence class of B. Show that the equivalence class of A intersect the equivalence class of B is non-empty. But this is pretty straightforward. Essentially, all that we need to show is that these sets are non-empty, right? Once these sets are not empty sets, then we know that they're the same, so they have to have some non-trivial intersection. So what property of a equivalence relation do we use to show that equivalence classes are non-empty? Well, it's reflexivity. So, we need to find an element of A. Since A is in the equivalence class of A by the reflexivity of R, namely A comma A is in the relation, right? Which tells you that the element A is inside the equivalence class of A. We must have A in B as well, since the sets are the same. If A is in the equivalence class of A, then A is in the equivalence class of B, thus the intersection is non-empty. Thus, A is inside the intersection of the equivalence class of A with the equivalence class of B. Great. And then to finish this proof, we'll show that the third statement implies the first statement. So we assume that there exists an S inside A, the equivalence class of A intersects the equivalence class of B, right? We start off by assuming proposition 3, so something's in the intersection. And what I want to show is that A comma B is in R. So by definition, this S is in the equivalence class of A and in the equivalence class of B, which means A comma S is inside the relation R and B comma S is inside the relation R. This is precisely what it means for S to be in the equivalence class of A, and this is what it means for the S to be inside the equivalence class for B. And now you can already see what's going to happen by symmetry. SB is in R, and then by transitivity, that yields A, B in R, which is what we wanted to show. Okay. Right, so what is this theorem telling us? This theorem is essentially a big part of this is essentially the theorem which tells us that the equivalence classes associated to an equivalence relation form a partition of the set. And I'll get to defining what a partition is in just a moment. Okay. So let's do the following. If R is an equivalence relation, oh, yep, on A, first note that if I take the union over all A and A of the equivalence classes of A, so I take every element of A, and to each element I associate its equivalence class. Note that if some equivalence classes are big, then I am unioning the same object with itself a bunch of times here. But that doesn't matter because the union of a set with itself is just that set. So this is going to be equal to A. Namely, every element in A is inside a unique equivalence class. We know it's inside some equivalence class because for any A, we can form the equivalence class of A, and we know that for any A is always inside the equivalence class of A, right? So maybe A is the only element inside the equivalence class of A. Maybe there's other stuff, but every element is inside some equivalence class. And the second thing is, this theorem tells us that the equivalence classes are disjoint. Either there's no intersection or they're the same. The moment that two equivalence classes share a single element, they're the same equivalence class, which means, in fact, that every element is inside a unique equivalence class. Okay, so by the theorem, right, I'll just write out by the theorem, if A is not equal to B, then the intersection, sorry, if the equivalence class of A is not equal to the equivalence class of B, then the intersection of the equivalence class of A with the equivalence class of B is equal to the empty set. Okay, so now we get to the point where we can say that this is a partition. This means equivalence classes form a partition of A. Of the set A. So here's the definition. A partition of a set A is a collection of subsets BI, so I get a collection of subsets BI for some index set I. Notice that I'm not assuming that I is countable here. I'm not listing them out one by one. I'm just saying there's some collection of BI such that each of the BI is not the empty set. The union of the BIs, I and I, is equal to A, and the intersection, BI intersect BJ, is the empty set for I not equal to J. Okay, there's a very nice picture for this, and it's similar to one that I drew yesterday. Let's assume that I'm doing a partition of a finite set. So the dots are the points in the set, and the equivalence classes are just ways of carving up the set into different chunks so that every element is inside at least one of these subsets. I don't know, I'm just having fun with this. Okay, so for instance, this would be some B1, for instance, and maybe this is B2. So every element is inside a unique subset BI, and you have a partition, and none of the BIs are empty. So the partitions are very, very broad. Very general. In particular, they don't need to follow any rule. Right? There are very few restrictions that are put in place by this definition. Let's do a partition of an uncountable set, say. Here's a partition of R. Let's do the following. Let's have the number 3 be one element, and then let's have the integers -3 be another subset, and then let's have the rational numbers minus the integers be another subset, and then let's have the irrational numbers. Right, this is some partition of the real numbers. Every real number is one of these 4. None of them are empty, and all of their intersections are trivial, right? 3 doesn't intersect z minus 3. Z minus 3 doesn't intersect the rationals minus z, and the rationals certainly don't intersect the irrationals. Okay, so what we have shown essentially is one direction of something important. That one direction being, for any equivalence relation on a set, you can form a partition of that set using equivalence classes. And now we show the kind of simple but important other direction, which is that any partition on a set can be used to build an equivalence class or an equivalence relation on the set. And in terms of this diagram, what should the equivalence relation be if I have a set and a partition on the set? Well, the equivalence relation should be that two elements are related if they're in the same partition, right? I should treat all of these elements in this partition as all being equivalent to each other. I should treat all these elements in this partition as being equivalent to each other. Oh, non-empty. Can't have any empty partition or empty subset of the partition. Okay, so conversely, given any partition, so any partition of A can be used to form an equivalence relation. Namely, A is related to B, AB is in R, if A and B are in the same BI, where BI is one of these subsets that follows these properties. Okay, so what we need to check is that this relation, which is well defined, actually is an equivalence relation. So we need to check our three things. So first, let's check reflexivity. So what I should start off by saying is let bi for I in I be a partition of A. And let R be the relation given by A, B is in R if A and B are in BI. So first we need to show that this relation R is actually an equivalence relation. First thing that we'll show is that it's reflexive. So let's assume that A is in BI. Remember, by the definition of a partition, every element is in some BI, so I'm taking an arbitrary element A, and I know by the properties of partition that it's in some BI. Then A is in R, since A is in BI. This is just saying that if an element is inside the partition, that element is inside the partition. But that's sufficient for showing reflexivity. So that follows kind of trivially. Let's check symmetry. Well, so let A be in R. So A, B are in some BI. But then BA are in BI. So BA is in R. So the symmetry follows. And lastly, transitivity. If A comma B are in, so transitivity. If AB and BC are in the relation, I want to show that AC is in the relation. If AB and BC are in the relation, what this means is that A comma B are in BI and B comma C are in BJ, right? These two being inside the relation means that both of them are inside one of the BIs. These two being inside the relation mean they're in one of the BJs. However, by BI intersect BJ is equal to the empty set, we see, or for I not equal to J, if we have B in BI and B in BJ, this means that BI is equal to BJ. Thus, A, B, and C are all inside BI, so AC is inside the relation. Okay, kind of basic to see, but this is actually a very deep and this is a very deep kind of structural theorem about sets, which is telling you that you can always go back and forth between equivalence relations on a set and partitions of the set. Okay. So the conclusion of this is the following theorem. Let R be an equivalence relation on A. Equivalence class is partition A. Conversely, given a partition of sets BI of A, um, there is an equivalence relation R on A whose equivalence classes are the BI. Okay, so this tells us we can go back and forth between equivalence classes and partitions. And now we can get to some examples, and I think these are kind of familiar. Um, what are the sets in Z given by congruent, say, modulo 5? So equivalence classes. Equivalence classes in Z under the mod 5 relation. Well, we've already kind of been through this. We have some equivalence class called 0, and this is going to be the set of all elements like -5, 0, 5, 10, 15, etc. We have the equivalence class of 1, which is equal to -4, 1, 6, 11, 16, etc. Right? These are all the things that are congruent to 0 modulo 5, or in other words, they're divisible by 5. Here are all the integers such that you have a remainder 1 when you divide them by 5. If you look at 2, then you're going to have -3, 2, 7, 12, 17, etc. 3, the equivalence class of 3 looks like -2, 3, 8, 13, 18. And lastly, you have the equivalence class of 4, which looks like -1, 4, 9, 14, 19, etc. Right? So we've already seen this sort of drawing of the equivalence classes um, for the relation modulo m for some integer m. And now the only thing that I want to point out is that these sets precisely form a partition of the integers. Every integer has some remainder when divided by 5 by the divisibility theorem. That remainder is either going to be 0, 1, 2, 3, or 4. And I'm just sorting them into some set based on what their remainder is. So the divisibility theorem ensures that every integer fits inside one of these sets. Moreover, the uniqueness part of the divisibility theorem says that these sets are unique. There's no intersection between the set of integers whose remainder is 0 modulo 5 and those integers whose remainder when divided by 5 is 2 modulo 5. They don't intersect. So this is a partition on the integers, and if I wanted to kind of go backwards, I could use this partition and say each of these are equivalent sets, and I would regain the equivalence relation of modulo 5 on the integers. Okay, let's do some other fun ones. So here's an example. So let's show that the relation R on differentiable functions f from R to R, looking at differentiable functions from R to R, and the relation is going to be f comma g is in the relation R if f prime of x is equal to g prime of x is an equivalence relation. Okay. So what are the things that we need to check to show that this relation is an equivalence relation? First, we should try to show reflexivity. And reflexivity is, I mean, all these are going to be very straightforward and obvious. Essentially, this is just asking, if I have some differentiable function f, Um, so let f be a differentiable function. Is it the case that f prime of x is equal to f prime of x? Here, this is for all x. Yes. F prime of x is equal to f prime of x. Thus, ff is inside the equivalence relation, R. So, this is a reflexive relation. Is it symmetric? Yes. If f prime of x is equal to g prime of x, then g prime of x is equal to f prime of x. So, if f and g is inside the relation, then gf is inside the relation. Lastly, let's do transitivity. So this is assume f and g are in the relation and gh are in the relation. So this first part is saying that f prime of x is equal to g prime of x for all x, and moreover, g prime of x is equal to h prime of x for all x. But then, since these are functions, and we're saying that the function g prime of x is the same as the function f prime of x for all x, and it's also the same as the function h prime of x for all x, we see clearly that f prime of x is equal to h prime of x for all x. So f comma h is in R. So this shows that this relation is indeed an equivalence relation. And it should be a pretty familiar equivalence relation. What is the equivalence class of a differentiable function? Like, for instance, x squared plus sine of x. What is the class of x squared plus sine of x? Well, it needs to be all functions which have the same derivative, and as we learned from calculus class, the collection of all functions with the same derivative as a given function are those that differ from this function by a constant. So this equivalence class consists of all functions x squared plus sine of x plus c. So this is in the equivalence class x squared plus sine of x for all c in R, right? If I change a differentiable function by adding any constant number, I haven't changed the derivative. And this is precisely the collection of functions that have the same derivative. Right? So here we can see that we can form a partition of differentiable functions, which is a huge, huge space, right? This is very far from being countable. It's an absolutely enormous collection or set. And now we're partitioning it by equivalence classes of what your derivative is. Great. So that's a nice example of equivalence classes. Let's see, do we have time for more? Yes. So as another example, let's let R be the relation on subsets. So it's the relation on the set of all subsets of the reals. So what I'm going to say is that I take S and T. So let S and T be subsets of R. S and T is inside the relation if S the cardinality of S is equal to the cardinality of T. Okay, so it'd be a good exercise for you to check that this is indeed also an equivalence relation. And we can ask some fun questions. For instance, what is the equivalence class of the set 1, 2, 3? Okay. So what is happening here is I'm looking at all the possible subsets of the reals, and I'm saying two of them are equivalent if they have the same cardinality. So the equivalence class of the set 1, 2, 3 is the set, so everything in this equivalence class is every subset of the reals which has cardinality 3. So this equivalence class is equal to the set of all subsets with cardinality 3. In particular, if I pick any random 3-element subset of the reals, like say 5 pi e, this is inside this equivalence class because it's got 3 elements. What is the equivalence class of z? Right? Z is a subset of the reals, so it's inside here, and I can form the equivalence class of z. So all the things that are equivalent, or everything in this equivalence class is everything that has the same cardinality as z. And z, as we know, is countable. So every countable subset of the real numbers is inside this equivalence class. So for instance, z greater than 0. Oh, sorry, countable but not finite. So z greater than 0 is inside this equivalence class. Z greater than 0 intersect evens, right? Positive even integers, also countable. So they have the same, and infinite, they have the same cardinality as z. That's another subset that is in the same equivalence class as z.